So what kind of minerals can be found in Wölsendorf? I was there with 2 colleagues to find uranium and antozonite. As before every excursion, it is important to be properly equipped. Sturdy shoes and in hindsight a helmet would also not hurt because it's all loose material on a slope. Not a great combination. Masks are important again this time, unless you get caught in the rain like we did. And of course I have my radio code 103G. With the discount code in the video description you can get 10% off. Of course I also got a UV flashlight and also all the other stuff that I showed you. These are quite recommended when doing a trip. Also, as before every excursion, you should check mindat.org to find out what has already been found here and where to look. Aha! So we are in the fluorite mining district and all of that can be found there? For all practical purposes the answer is unfortunately no. These may be microscopic findings. You can see that the area was used mainly for barite and fluorite, so it stands to reason that you can still find them there today. But it's always worth looking at your own finds on a microscope. So here's a tip that I forgot to mention in the last 2 excursions. Wölsendorf is located in the TBE area. Vaccination before going in such an area is highly recommended. Before I give you the exact location, please don't do this alone. Be equipped, loose rocks on a slope, well you know that's not a good combination, and everything is at your own risk of course. Better safe than sorry. Right at the slope you are greeted with these interestingly colored rocks. With the radio code you can verify that these purple to black spots contain radioactive material. It is uranium that causes the radioactivity. The base material is actually fluorite. Chemically speaking, fluorite is CaF2 and it's colorless in its pure form. However, this material is purple and this has something to do with the radioactivity. Enclosed uranium destroys the calcium fluoride crystal lattice through its own radioactivity, causing color defects in the crystal. This special type of calcium fluoride colored purple by radiation is called antozonite. Occasionally you can also see veins like these. They give us a clue as to how the antozonite got here, namely of hydrothermal origin. So a long time ago a hot solution of calcium, fluoride and uranium ions and in the surrounding granite, first the uranium, later then the still colorless fluoride could crystallize out from the hot solution as it cools. And finally we also had crystallized barite. The geologists call this epigenetic origin. So in other words, when the surrounding rock was already there and had cracks, and these cracks provided space for a new mineral to grow afterwards in there. Over time the fluoride was irradiated so strongly by the existing uranium that it turned purple. And people gave the mineral the variant name antozonite or sting spar. And parts of this slope contain so much uranium that my radio code consistently reads 400 CPS. In such cases, it is sometimes worth using a Geiger-Miller counter, which is better at measuring beta radiation, which have a shorter range, allowing you to locate the source of radiation a bit easier. If you hit this purple material, you will soon notice a very unpleasant smell, and I would really recommend to anyone to try this, just for the experience. It shows very impressively where antozonite got its nickname, sting spar. And at this point, here's the go-to story why chemistry nerds like me like this mineral so much. Due to the uranium contained in the fluorite, not only can radiation damage occur in the form of lattice defects, but since the radiation is ionizing, the fluoride ion can also be ionized, thus producing elemental fluorine. An element that is so highly reactive in its pure form that it was long believed to only occur as fluoride ion in nature. Until our favorite fluorine chemist, Professor Krauss, together with Dr. Schmid and Dr. Mangstel, was able to prove that this highly reactive form of the element is created in the crystal lattice and remains trapped there. This was determined using solid-state fluorine-19 NMR spectroscopy. However, this is not the stinky smell that I always describe fluorine with, as being burnt rubber with a bit of chlorine smell. I find that smell of broken antozonite has a slight sweeter note to it and is not as pungent as chlorine. The paper also explained that the sweetness comes from ozone, and now that I have smelled sting spar gas and fluorine gas out of the cylinder, I can only agree with them. So the ozone could well be a reaction product of the fluorine released into the environment reacting with, for example, moisture. At first I thought this bag was a historical relic from the construction of the highway behind us, but the comments on the German version of this video pointed out that it was probably the result of illegal mining activities, which that's not good. I have to say that this passageway shows a little too much activity to just be enclosed uranium. It is possible that there is also some primary mineral present. What you sometimes see laying around are these orange stones. They don't have to be this intensely colored, but it's better to be cautious with them. At first glance and without radiation meter, I can't distinguish between iron oxide and toxic uranium secondary minerals. I found it very interesting and wanted to show you what to look out for when collecting in Wölsendorf. While collecting, we met two curious people who also wanted to know what was going on there. Greetings to Ollie and Matthew. With my bags half full, I was now heading to the lab. So it's mostly granite. I think it's pretty easy to recognize if you're interested enough to look up a YouTube video about Wölsendorf minerals. And granite contains feldspar, quartz and mica. You can find purple to black chunks like these in large quantity, also known as stingspar. It is a special type of fluorite. Feel free to take it with you. It's really not that hard to find, and the radioactivity emitted by the mineral does not pose a significant risk. There's no need to worry about radioactive contamination here. It's pretty much completely harmless. As you can see, I didn't bring a normal piece with me, but one with a green banding. But this is low quality material. It's still a nice souvenir, but if you really want to take home something cool, look for crystals. This is where it can get a bit tricky because you'll also find smoky quartz there. In comparison, you can see that both sparkle beautifully, and you should definitely take both of them home. But antozonite, like all the other fluorites, occurs as cube-shaped crystals. With small ones, it can be quite difficult to tell them apart, as the cubes may also have grown on the side of the rock. Quartz and smoky quartz have hexagonal basic structure that tapers to a point at the top. So we are differentiating between hexagonal columns with a point tip as opposed to small cube crystals. This is how you can distinguish fluorite from quartz, or in this case, antozonite from smoky quartz. Let's move on to the smoky quartz. Smoky quartz is a variant of a very well-known mineral, quartz. Silicon dioxide. Smoky quartz is formed when quartz with aluminium impurities is exposed to high levels of radiation. For example, when it grows next to uranium. And as I already mentioned, there is a lot of uranium in this area. Depending on the degree of discoloration, we no longer refer to it as smoky quartz, but rather as morion. So now we talked about fluorite that has been exposed to radiation and quartz that has also been exposed to radiation, and now we finally come to the source of the radiation. Uranium minerals. In Wölsendorf, unlike in the Erzgebirge, uranium is found not in its primary mineral, but in the form of secondary minerals. This means that caution is required here, as secondary minerals greatly increase the risk of radioactive dust and contamination. For example, you can see how radioactive our washing water was. We simply dumped it back on the side there. In any case, it looks very nice. Some smaller crystals can be found in the granite. With a little practice, you can see the uranium minerals in the granite with the naked eye, but UV light is nicer. If you're lucky, you'll see crystals like these. First, the short version. We are unsure about the fluorescent minerals. The safest name for this mineral would be a uranium mica, but there are dozens of different types of uranium mica. With a gun held to my head, I would guess it to be Heinrichite, but it would be safer to just call it uranium mica. I'll just say that the fluorescent minerals you can see here are simply poorly developed specimens of this mineral. The entire analysis in the next few minutes was done using this crystal as representative of fluorescent parts of the mineral. We will take a closer look at another sample in the analysis, namely this specimen, which is representative of all the non-fluorescent but nevertheless radioactive coatings that can be also found there. Here I estimate it to be calerite or uranospinite with iron oxide, and I will now explain in more detail how we arrived at this estimate. Fortunately, I have access to a laboratory for analysis, and I was able to analyze the elemental composition using X-ray fluorescence. The XRF camera belongs to Professor Dr. Gregor Stab. Thank you very much for allowing me to use this for my analysis. I have explained how the measurement works in more detail in this video. In short, a sample is irradiated with high energy X-rays. All of the elements contained are excited and then relax again, emitting very specific radiation. This allows us to detect whether an element is present or not. Further conclusions require more analysis and calculations. Now it gets a little complicated, because here we encounter the first problem. In the first analysis of this sample, it turned out that silicon was present along with some uranium, phosphorus, calcium and barium. Based on the silicon alone, a thought occurred to us. Might have just been that we also measured the mineral underneath it. And I really don't know what the fluorescent mineral is. So unfortunately I had to break off the crystal. This somehow goes against my idea of using XRF analysis as a non-destructive method, but well, here we go for science. In a second attempt, this mineral again shows uranium, barium, arsenic, and I had the software searching for calcium and magnesium. Unfortunately, magnesium was causing a bit of problems, so I will just completely ignore the percentages. They are influenced by the misinterpretation of magnesium. So what do we know so far? We have analytical proof of the presence of some of the elements I just selected for. We know that it's a uranium-containing mineral. We can tell from the crystal form that it's a layered mineral and it's easily cleavable. Good cleavability plus uranium means to us that this is a uranium mica. This is also the most accurate description of this mineral, in which I have not yet made any mistakes in the interpretation. If we wanted to be more specific, what types of uranium mica are there? First, let's take a look at the chemistry of the most common uranium minerals. We often have a doubly positive metal ion, then the uranyl, and then a tetraoxo anion with pentavalent central particle. I told you, it is going to be complicated. So, the tetraoxo anion of the fifth main group. And if we narrow it down further, nitrates are out because they are not tetraoxo anions. They only have 3 oxygen instead of 4. And this all is not the definition of a uranium mica, but I wanted to convey some chemical systematics in a video like this. This leaves us with phosphorus, i.e. phosphates, and arsenics, i.e. arsenates. Stibates occur, but they are very rare in the context of uranium. And now we have the variable here in front of the composition. Divalent means the most common alkaline earth metals, since they are always divalent, i.e. present as 2+ ions. But we can also have copper or other transition metals. There are others, but these are the most common. Minerals always are divided into mineral classes. And here we are talking about the phosphates, arsenates and vanadates, and more specifically the family of uranyl phosphates, arsenates and vanadates. These belong to the uranite group, i.e. uranium mica, according to Strunz. Let's leave the phosphate anion and add magnesium. Then we would have saleite or saleite. If you go down one element in the main group, we have described autunite with calcium uranyl phosphate. Hydration changes on contact in air, so I won't go into further detail about this. I'm not familiar with strontium in this context, and barium would be uranosicide. If we take arsenate and then start from the top again, we would have described novacekite with magnesium uranyl arsenate. The calcium analog would be uranospinite. Yes, these are all very beautiful pictures which I did not take myself, but which are from a highly recommended website called Mineralienatlas. With barium as the cation, we would have described heinrichite. That would cover the main group cations. But what about the other metals that can also be used as 2+ ions? Copper uranyl phosphate would be taubonite, and the arsenic analog would be zoynerite. Even though they are extremely pretty and belong to uranium mica, since the copper uranyl mica do not fluoresce and our mineral does, that means our mineral can't be zoynerite or taubonite. And if you knew how many uranium micas I just left out, there are iron 2 uranyl phosphates, which I can't pronounce, cobalt 2 arsenates, and many more. But they are also not listed on Mindert as minerals that can be found in Wölsendorf. So I doubt that we just discovered something new. What makes the identification even more complicated is that all of these uranium micas are so similar that they can form mixed crystals. Or different uranium micas can also grow together. Such epitaxis cannot be distinguished with XRF analysis. And I myself am not a mineralogist for whom such identification is daily bread. So let's leave it at fluorescent uranium mica and exclude it being taubinite or zoinerite based on its fluorescent. A lot of fluorescent minerals, but now onto the non-fluorescent uranium stuff. That was a curse to me. Dusty uranium that has settled onto a mineral, settled both onto antozonite and on the smoky quartz. I cannot scrape it off for XRF analysis, and here's a spectrum of the uranium grown on quartz. This is where the silicon comes from. We can also see peaks of iron, arsenic, and uranium. An iron uranyl arsenate would be Fluorite. However, it could also just be that another uranyl arsenate with an element not visible in the XRF has settled onto the quartz alongside some iron oxide or hydroxide. Sasha collected a few more samples and sent a photo of them to me, and at least we can guess from the structure of the mystery mineral that it looks somewhat radiating and not layered in structure. That would imply that it might be uranospinite, which occurs parallel with some iron oxide. However, we do not have an XRF spectrum of this sample, but it comes from the same location, because he went there more than twice. I doubt that it's a sulfate as suggested by the XRF, because even if the software says yes, sulfur, that peak does not match. They don't match phosphorus either very well. Calcium on the other hand is possible, so in summary, my best guess would be uranospinite with some iron oxide or Fluorite. Both minerals that are not listed on MinDat. But that's just a guess from me as a non-mineralogist or geologist based on XRF analysis and eye spectroscopy. I could imagine subjecting one of these specimens to a more detailed analysis if our geoscientists feel like it. Further results will be added in the video description if they are not worth their own video. Bonus, I also found a crystal of light yellow minerals. These are surrounded by purple fluorite. The XRF analysis suggests that I have absolutely no idea what this is. I measured it at 2 different points, and first I thought it was barite and barium and sulfur are present, but their contents are so different that this cannot be the whole truth. The second measurement suggests a zinc sulfide modification, whereas the first suggests a phosphate. The calcium may come from the fluorite. Under 365 nanometer UV, parts of the mineral fluoresce orange or red. I'll just call this a complex mineral compound. And now we know what can be realistically found in Wölsendorf. I'm very happy with my findings, and I hope that you now know what characteristics to look out for. I must say that I would have loved to find some Wölsendorfite, but who knows, maybe I'll find a good deal for this mineral someday. A huge thank you goes out to Professor Dr. Gregor Stab from the Department of Classics, who let me use his XRF camera, and to Sasha for organizing and Benedict to coming along with me, and greetings to Ollie and Matthew, and of course a special thanks goes out to my Patreons for the financial support. With that being said, thank you for your attention and goodbye.